Right, we are on day 2 of our exponential functions, and today we're looking at a special base, and that base is e, which is our natural base, which comes from Euler's number. Now, Euler's number is kind of like pi. It's a constant, but it's irrational, so we always represent it using e in our calculator. Just like we use pi on our calculator, we can use e on our calculator. So the graph of e to the x power looks like our other exponential graphs. Our domain is all real numbers, our range is positive numbers, our y-intercept is still at 0, 1, and it's an increasing function. So we use e when we are looking at problems that have to do with interest and continuously compounding interest. So first we're going to take a look at a radioactive decay problem, and then we are going to look at those interest problems. So after t years, the remaining mass of 10 grams of a radioactive element whose half-life is 25 years is given by this formula. Now, half-life means that every 25 years, half of the matter that we started with has decayed. So we have half left that we started with. So if we are looking at 25 years, how much of the initial mass remains after 25 years, we should have half of what we started with. And if we started with 10, then we should get 5. So let's test this out. So if t is 25 and we plug that into the formula we're given, we are going to be able to do this without a calculator because 25 over 25 is 1. So that's 10 times 1/2 to the first power, which is just 10 times 1/2, which is in fact 5 grams. So that is our half-life, radioactive decay. Half of it is left after 25 years. Okay. Now the good stuff that you really care about, which is money. So compound interest. Our T represents years. Our current balance in the account is A. P is our principal. Annual interest, which we put in decimal form when it's in these formulas. And then our N is the number of times it's compounded per year. So here's our formula for number of times compounded and compound interest. And when it's continuously compounded, that's when we use our E constant. So jumping into an example, on this example 2, $1,000 is deposited into an account for 9 months at 12% interest. So our principal value, the amount we're initially putting in, is 1,000. Our interest rate is 12%, so as a decimal that would be 0.12. And time we always put in years, so if it's 9 months out of 12 years, that's 3/4 or 0.75. So what's the total amount in the account if we were using a simple interest account, and we're given that formula here, so let's figure that out. Our principal is 1,000, 1 plus our interest rate times time, and we are going to use our calculator for this. And all of these types of problems, when you're putting them in your calculator, it's really important that we are using parentheses so that we know the calculator is giving us exactly what we're asking it for. And so for simple interest in 9 months, that would give us $1,090. Now, let's look at what it would be if it was a compound interest account and see why that might be the better option with our money. So if we're compounding quarterly, that means 4 times a year, so n would be 4. And the formula we're going to use is that first one that we were given. So we're looking for the amount in the account when we have a principal of $1,000. Our interest rate is 12%, compounded 4 times a year, and we are talking about it being 0.75 of a year, so 9 months. So again, in our calculator, and we get $1,092 and about 73 cents. So already you can see that this is yielding us more money than if we had it in a simple interest account. Now let's look at if it was compounded continuously. So we are going to be using that other formula that has E in it for this one. So we're looking for the amount when we had $1,000 principal, compounded continuously, 12% interest, for 9 months. Now this is where we need our E button. So the E button, if my camera will focus, is down below on the LN ln, that blue e to the x power, so you go second, ln, and it pulls up our e. And there we go, about $1,094.17. So the type of account that gives you the most bang for your buck is going to be one where you have continuously compounding interest. All right, on to example 3. If we have $10,000 invested with an annual interest rate of 7.5%, so this is our principal, this means that R is going to be 0.075. Compounded monthly, that means that N is 12. Find the balance in the account after 10 years. As we're given a value for N, that means we're going to have to use that formula with N in it. So the amount in the account with $10,000 principal, our interest rate is 0.075, compounded monthly over 10 years. Again, being really careful about our use of parentheses in the calculator. And we end up with $21,120 and change. All right, last problem. If we are investing $15,000, that is our principal. Annual interest rate of 8%, that means that R is 0.08. Find the balance after 6 years, that means T is 6, if we're compounding quarterly, monthly, continuously. So we're going to compare those three values. If we're compounding quarterly, that means that N is 4, and we're going to be using that first formula that we looked at. So the amount, $15,000 principal, 8% interest compounded quarterly over 6 years. That's going to give us about $24,126.56. Then if we're compounding monthly, that means it's 12 times a year because there are 12 months in a year. So everything in this equation is going to stay the same except for N. And hopefully you're gathering that doing this, we should be having more yield in our account after that same amount of time when we're compounding more often. And that does give us a little bit more. And then lastly, if we're compounding continuously, we're going to have to use our other formula without N. So the amount in the account for $15,000 principal with the same interest rate after 6 years. Using that E button again. And that gives us the most amount of money out of all three potential accounts. All right, one last thing I want to point out to you so that you are able to do your homework is we have these two formulas where we're plugging in our principal value and we're getting the amount in the account after a certain amount of time. But if you were asked the question the other way around, where you're given the amount in the account and you're asked to find the initial principal that you invested, you can take these same equations and what you'll do is divide A by everything that's not P. So your principal for a continuously compounded interest account would be A divided by E to the RT power. And when we're compounding by a certain given amount, same concept, you're going to divide A by everything that's not P. So A divided by 1 plus R over N to the NT power. So you're just reworking that same formula to find P instead of A. And that is it for today's notes.